Okay, so we're going to look at uniform motion graphs. And in physics, we use graphs, well, any kind of science course really, we use graphs to give us all kinds of information. And what's on that graph tells us even like what formula we're doing or what's happening. When we are doing calculations with graphing questions, remember three things. What's on the axis? Those are the important pieces. What's the slope of the graph? And you always need 2 points on the graph of the slope. And do we want them to be close or do we want them to be far apart? Far apart. And do we want it inside of our data or outside of our data? Inside of our data. So it comes from the line of best fit, not our data points. And we need that triangle to be as big as possible. We saw that with Daniel and Kyle when they did theirs. Daniel's graph was really close. Kyle had other errors, but make sure your graph is as far apart as it can get within the data points that you collected. Okay? This is really key. Don't use formulas for graphing. We're going to use this. How do we solve for slope? How do we solve slope? So close, Kyle. Let's go y2 minus y1 over x2 minus x1, otherwise known as your rise over your run. Okay? Change in y over change in x. There's any number of ways of calling slope, but the calculation is y2 minus y1 over x2 minus x1, but it's called rise over run. Somebody asks you, how do you calculate slope? Rise over run. Change in y over the change in x. Okay? So slope tells us a piece of information. It's usually used when we're putting it back into our linear equation. But the area under the graph, that also tells us a bunch of information. And so it's always in reference to the x-axis, and you have to maybe like break up the area because it might be something like this. If you had a plot and you would simply just do your triangle, this one would have a little bit like this, and then a rectangle, and you would have area 1, area 2, area 3, and you would add those all together to get your total area under the graph. And so if I'm looking for area of a rectangle, how do I figure that piece out? How do I figure out area? Length times width. How about for a triangle? Base times height divided by 2. Or you might know it as 1/2 base times height, however you want to figure it out. Okay. Uniform motion, what does that mean? Daniel, you're the one who came up with the definition yesterday. Constant speed or constant velocity, depending on if we're looking at displacement or distance. If I'm looking at distance, and this is my XY graph, what's going to be on my Y, do you think? I sure can. What do you think is going to be here on my Y-axis? Distance. Typically, it's measured in meters. So this then must be time, typically measured in seconds. Okay? If I have a graph that looks like this, these lines tell us something very, very important. How do we calculate distance? Do you remember? How do we calculate distance? Look back in your notes if you have to. It's the sum, right? Of all the different distances that you walk, it's the sum of it. So if I was doing this, my time is increasing this way, my distance increases this way. What could you say about this? About the speed? Because speed is equal to distance over time, and velocity is equal to displacement over time. So what could you say about this piece right here? He's which? He's what? It's positive, yeah. What else can we say about it? Is it a steep slope or a very shallow slope? Is it a steep slope or a shallow slope? It's a one answer question, people. It's a shallower slope. Okay? What can we say about this? As the time is increasing, the distance is increasing. So is this object in motion? Yes. So we can say that maybe this object is moving at a slower speed. We can say that about that slope. What about this piece right here? What can we say about that? Time is increasing. He's not covering any distance. So if you're not covering any distance, are you moving? In science terms, that's called being at rest. Now, what about this? Kyle said that this was a positive slope, and in math, this is a negative slope. But distance is added. It's the sum of the distance. So is this object in motion? Time is going on and something's happening with the distance. Is this object in motion? Yeah, this object is in motion. This point right here, this is a change in direction. That's a change in direction. So if I know that this is a change in direction and distance is the sum of, is the object moving faster or slower than it was here? Faster. Because why, Avery? Because it has a steeper slope. Okay? Let's look at a velocity time graph. So if this is velocity, what is this piece here? Displacement. And this is still time. So if I have this here, actually I'm going to change this up just a little bit. All right. What is displacement? If distance is the sum, what is displacement? Look back in your notes if you have to. A change in the direction of movement. So if we're moving east and then we go west, we subtract those two differences, or those two values, right? Okay, so then what's going on here if I have a flat line? Because over here, I said it was at rest when it was a distance time graph. What does this line mean when it's a displacement time graph? The velocity isn't changing. When I have a flat line at some displacement value, okay, this is at a positive displacement value. When I have a value there, I have motion because there's direction. We're moving in a specific direction. Here, this is just movement. This is movement in a direction, so I need to have a line at some displacement value. Okay? What about this piece here, from here to here? What do I have there? If I'm telling you that this is in motion because I have something happening with some displacement, here I'm at what? 0. So do I have displacement? Do I have motion? No, I have no motion. So this is at rest. Okay? This is at rest because there is, remember, displacement is the change in. I have to have more east than I have west, or I have to have more west than I have east to have motion. If it was at 1, if it was sitting right here above the line, that would be in motion. When it's right at 0, that means that I've had my forward distance and my opposite distance have negated each other. So I have no motion. It's a hard concept to think of because you have to go somewhere and come back the exact same distance to have velocity, because it's the change in. Okay? What do I say about this piece? It is going in the opposite direction, and right here was the change in direction. So now instead of going lots east and a little bit west, now I've gone a little bit east and I've gone a whole lot west. Okay? And I've totally made an error, but it still works. I totally made an error because I didn't even pay attention to the title. What does the title of the graph say? Velocity. And Mrs. Pyre just wrote down displacement. That might make a little bit more sense in your brain, Avery. Okay? Same concept though. There's still motion here. They're still at rest here. There's still motion here. If I was to look at, so here if I looked at slope, On this graph, the slope tells us speed. In here, what is the area going to tell us? If I look at area being length times width, what's my length? Pick an axis. No, like what are these? Oh. Velocity, right, is on my y-axis, and I multiply it by my width. I could say time, I could switch them, it doesn't matter. What is velocity times time? What is velocity times time? So my area is going to be equal to my displacement. Okay. So here slope is equal to rise over run. My rise is my distance. My run is my time. And so my slope is going to be equal to speed. Over here, knowing that area is length times width, my length we said was velocity, and my width is time. And so I'm discovering what? Velocity times time, displacement. Okay? So in the first one, an object is at rest when the graph is horizontal, whereas in this one here, an object is at rest when the graph is on the x-axis, so velocity equals 0. Over here, an object changes direction when the graph changes direction, and over here, an object changes direction when the graph moves from positive to negative, or negative to positive. Okay? Clear? Even though I made the mistake, does it still make sense? Thumbs up, thumbs sideways, thumbs down. So that would be a sideways, CJ. Okay, let's look at some examples. This will help. It says, use the following graph of the motion of a sailboat to answer the next questions. The sailboat was initially heading east. Perfect. What does it say on the y-axis? Distance, and it says on the x-axis, time in hours. So when we look at this, which section of the graph shows the sailboat having the greatest speed? C to D. Why do you say C to D? As the steepest slope. Does it matter that it's a downward slope? Nope, because it's distance. It's the sum of. What time does the boat change direction? One and a half. At which point? A, B, C, D, or E? C. So point C, which is approximately 1.5 hours. Okay. At what time does the boat come to a stop? So from B to C, which is a what time? 1 to 1.5 hours, right? All right. So now it's saying calculate the sailboat's velocity at t equals 2.5 hours, and it says record the answer to 2 significant digits. So velocity is going to be what? displacement over time, okay? In my notes, it's saying scalar. So either the question is asking for speed or they're miswriting it down. But we're going to be looking at, because this is a displacement time graph, this is a d versus t graph, y, change in y over the change in x is slope. And our slope is going to tell us what? Speed. So here I know that I can calculate this from the slope. So at time is 2.5 hours. So let's look. What is this? 2.5, okay. 2.25, right here. This is 2.5 hours, right there. We cannot take the calculation right at 2.5 hours. I'm going to tell you this right now for simplicity's sake. We cannot calculate time at 2.5 hours. That's called instantaneous velocity. We don't explore that for another unit and a half. So how would we calculate slope? We would take a point above Let's take a point above and a point below. Now these aren't lines of best fit, so we can take this data. So slope is change in y over the change in x. Change in y is calculated by how? Let's say it again. y2 minus y1. How do I figure out the change in x? x2 minus x1. Okay, so y2, this is going to be, this is 2 and 5, and this is 3 and 0. So y2, remember we read from left to right? We're going to have 0 minus 5, and we're going to go 3 minus 2. And what do we get for a value? Negative 5 over 1. This is kilometers, this is hours. So we get negative 5 kilometers per hour. This negative is a very, very important piece of information. So we calculated out the value. We got 5 kilometers per hour. This part tells us record it to 2 significant digits. So I would say 5.0 kilometers per hour. And when I go up to the main part of the question, it says that the sailboat was initially heading east. If I have a negative value, this is a change in direction. So what direction is my sailboat going? West. Nope, the negative, you can do it one of two ways. You can leave it as negative 5.0 kilometers per hour, which indicates that there's a change in direction. Or you would say 5.0 kilometers per hour and indicate the opposite direction. Either or, but don't do both. Okay? So in the question, it's asking for velocity. And did we figure out velocity? Yes, because we put a direction in there. Okay? Let's keep looking. E is a continuation. I'm just going to move the graph down so that we can still see it. It says calculate the distance is scalar, traveled at t is equal to 2 hours. So here is t being equal to 2 hours. So the distance covered, remember, distance is the sum. So from point A to B, how much distance did we cover? Well, let's look. Here's A. It starts out at 5, and it goes to 10. So what's the distance covered? 5. From B to C, how much distance was covered? None. And then from C to D, from here to here at 2 hours, how much distance was covered? 5 kilometers per hour. And so distance, then, what's the distance covered? 10 kilometers. Distance is the sum, right? Displacement. Okay, and it says to 2 significant digits, 1, 2. So my answer is good. What happens, let's look at Avery's. What happens if it asked us for displacement? Point A to B went how many kilometers? 5. B to C went how many kilometers? None. And C to D went how many kilometers? Why do you say -5? Because it went in the opposite direction. If I add these up, my displacement ends up being 0 kilometers. That's the difference between displacement and distance. Distance is the sum. It doesn't matter which way you traveled. Displacement matters on direction. Okay? Now it says, when it focuses, calculate the average velocity between time 0. Let me just move this up a bit. Between time 0 and time 3 hours. Record your answer to 2 significant digits. So remember that average velocity is equal to the total displacement over the total time. So we have figured out the first 3. We figured out A to B was 5.0 kilometers. We figured out B to C was 0 kilometers. We figured out that C to D was -5 kilometers. And what about D to E? What's the distance there that was covered? -5. Whoops. This is a negative, not positive. Okay, and the total time is 3 hours. So 5 plus -5 plus -5 gives me -5 kilometers over 3 hours. What do I get for a value? Somebody punch it into their calculator. Negative 1.66 repeating. Kilometers per hour. Okay, it says record my answer to 2 significant digits. So 1, 2, that's going to have an effect. So I've got 1.7 kilometers per hour. But then I have this negative sign. The negative sign is indicating that we're in the opposite direction from where the sailboat started. And the sailboat started out heading east. So what's my opposite direction? West. Okay? Make sense? Thumbs up, thumbs sideways, thumbs down. Up, sideways, you're up. Okay? All right, let's work on these practice questions. Page 27 of your question booklet, 18 to 20, 22, 23, and 25. I'm going to stop